Hello, welcome back. To our course on fluid dynamics, specifically fluid dynamics for astrophysics. So I figured I would take a few minutes to recap what we did yesterday. I felt I might have gone a little fast, and also, it's important to recap things, the overall philosophy of what we're going to be talking about at the beginning of a course, so that the basics are well set in your mind. So one of the first things we said yesterday is this word called continuum. Continuum mechanics, as opposed to the mechanics of a point parcel, like a rock or something. And so the forces acting on a rock, say an F equals ma for a rock, right? So you idealize the motion of this by considering its center of mass, something like that, and you solve F equals ma for that. This would be essentially the momentum equation for such a discrete particle. However, when we're talking about a continuum, we're not talking about such a situation. We're talking about the dynamics of an aggregate of particles, right? So suppose you have lots and lots of these particles, lots and lots of these particles, and you are talking about the dynamics of the aggregate of everything within this box. What is its F equals ma? And we're not talking about putting a center of mass to this and following only the center of mass. No, we're not. And that's not what we're talking about. We're talking about the dynamics of the aggregate of these particles. And so that is really what talking about continuum is all about. And as a visual aid to understanding this, think about holding a microscope, and going really close to, say, a box containing molecules of gas. Think of the molecules as being colored so that you can observe them easily. Now, in which case you're able to, when you're holding a very powerful microscope to the molecules, you're able to see the individual molecules, say, zipping around. And you could follow each molecule around, write an F equals ma for each of those particles, and follow the dynamics of them. Now either you move far away, or you remove the microscope, so that what you're really seeing is a bit of a fuzz. So you're really seeing a bit of a fuzz. So the individual nature of each of these molecules is lost, and you really want to know how a small portion of this fuzz, something like this, how this is behaving. So this is what one means by studying the continuum. It's the dynamics, or studying the properties, or studying the dynamics, say, of an aggregate. This is what I mean by dealing with continuum mechanics, right? So before doing that, I want to say a little bit about how, like we said, we are not following the dynamics of each individual particle, right? We are following the dynamics of the continuum. But things like number density, which would be a number per, say, centimeter cubed or meter cubed, depending upon what your favorite convention is, or things like pressure, temperature. These are familiar things to you when you talk about fluids. I mean, it makes sense, for instance, to talk about the temperature of gas in this room, to talk about the number density of gas in this room. Either it's so many particles per cc or something else, in which case you make a comment about whether the gas is dense or not so dense, whether it's hot or not so hot. So in order to go from, so it's important before studying continuum mechanics to at least, which is what fluid mechanics is, to have at least some appreciation of how these macroscopic quantities, both of these are macroscopic quantities. Right? So it's useful to have some appreciation of how these some of these macroscopic quantities arise from the properties of the microscopic molecules or the microscopic constituents that make up that make up the continuum, right? So what I'm now going to do is introduce the concept of a distribution function, which I'm sure you're familiar with what a distribution function is. So a distribution function, you can say that, for instance, the definition of this distribution function is this: the total number is equal to the integral of f d cube x d cube v. So I could simply say, and this is just total number, a dimensionless quantity. So what's the distribution? What's the definition of the distribution function? Well, this is the definition of a distribution function right here. Okay. Another kind of definition would be if you talk about number density, for instance, which would be number per centimeter cube. What I do is I integrate f only over d cube v, in which case this f, one example of such a distribution function would be the Maxwell-Boltzmann distribution function, which you're quite familiar with. Yeah, a distribution function for which the velocity would be on the x-axis and the distribution function would be on the y-axis. There are several interpretations, and this would represent, say, the probability of finding the number of particles in a certain you are so likely to find this many particles in this particular velocity range. That would be the physical that would be the physical connotation of this distribution function. Now, having defined, we will focus a little bit upon this particular definition. Having defined a distribution function like this, or for that matter like this, now this would be what's called the zeroth moment of the distribution function. Yeah. So now, what if I want to, this? Okay, let me erase this, and I will. What if I want to find out the average velocity? The average velocity of particles inside this kind of the average velocity of the molecules in this room, right? For instance, and so the average velocity would be, instead of here in particular here, really you can think of having a v raised to 0 here. That's as good as 1, because so instead of 0, suppose I stuck in a v raised to 1, yeah, and then I wrote f d cube x d cube v. This gives me the average velocity. So this is the number 1. If you're, this is not a prime. If you wish, I'll just erase it just to not confuse you. So the average velocity would be v times this, and you can think. So this is essentially the first moment. I call this the first moment because the power here is 1, and this is the 0th moment because the power here is 0. And so when you take the first moment, you get the average velocity, and the dimensions of this are, of course, centimeter per second. Yeah. If I want to take the second moment, the average of this, I just do that. And here, this is a very useful quantity. This gives you the mean squared velocity, and you just stick in a half m, sorry, beg your pardon, I do that, and I stick in a 1/2 m here, and I get a 1/2 mv squared, and of course I have to stick in an m/2 here also. So what is this? This is the average kinetic energy. Yeah. So you notice how I'm able to, and this is a macroscopic quantity, right? This characterizes the continuum, not this is an average quantity. Okay. And what is the average kinetic energy? I know from other considerations that the average kinetic energy is simply equal to This is simply equal to, right, and where this is the Boltzmann constant, the Kb is the Boltzmann constant. So here you go. So here you see I'm able to, so simply by altering this v raised to 0 to v squared, and of course sticking in a half m on both sides, I'm able to get a macroscopic quantity that you would normally associate with a continuum of gas, such as temperature. And once I have the temperature, I can also get the pressure. P equals N K B T. This is the first moment. Well, not quite the first moment. You don't integrate over velocity. You only integrate over. You integrate over velocity. You do not integrate over. Let me not make a mistake here. N would be integral of f d cubed v, right? And so this would be number per centimeter cubed. And this is the quantity that you're talking about here. So you get this from the microscopic distribution function. You get this from the microscopic distribution function like this, yeah. And at the end of the day, you're able to construct a macroscopic, quantity like pressure. And this is valid for the continuum, right? Not for the individual particles. It will be very expensive computationally to be following the individual particles around. That's not what we are interested in. We are interested in the dynamics of a continuum, and for that we need to know, average quantities such as the average velocity. Is there an average velocity of gases in this room? In other words, is there a breeze flowing through this room or not? Yes or no? The answer can be either way. What's the temperature of this room? How can I figure that out from the from the properties, from the kinetics? This is how you figure it out. So I wanted to at least bring this to bear a little bit before going on to actually studying fluid mechanics, because we will be talking exclusively in terms of quantities like the density, temperature, pressure, which are all average quantities, but it's important to know where these came from. Yeah, physically, as you know, the pressure, if you want to relate pressure to kinetics, the pressure is essentially a statistical average due to lots of molecules of pressure on a wall of a container, for instance, is the result of lots and lots of molecules striking the surface of the wall, right? So that's the physical picture you have. But nonetheless, how do you construct the pressure? This is how you construct the pressure. So I thought I would talk a little bit about, I'd reinforce this concept of how to derive macroscopic quantities from the microscopic kinetics. That was the first thing we did yesterday. And the next thing we did, before moving on to actually studying fluids, I figured I would say something about how a fluid, which you normally think of as either a liquid or a gas, most of the time in this course we will be implicitly thinking about a gas. Okay, but how, for instance, haven't you ever wondered how a solid is fundamentally different from a fluid? Yeah, the answer there is the most simple-minded answer, and there are lots of complications to this, but it's important to stick to the most simple-minded answer. And the answer there is the ability fluid. Their inability to resist shear. Under the influence of shear, even an infinitesimal shear, they flow. And this is what fundamentally differentiates fluids from solids, and we talked a little bit about what shear means. Essentially, you think of a surface, and if there are two kinds of stresses, two kinds of force per unit area you can think of. One is a normal, so there's the area element, so the normal is like so. So one is a normal force like this. Yeah, and so you are applying a normal force, and the force per unit area would be simply the result of this normal force. The other kind of force you can think about is when the force is tangential to the area, to the surface element, like so or like so. and these are called shear stresses. This is called a normal stress, and this or that is called a shear stress. So if you have an area element like this would be a normal force. So a dFn over dAn, this would be a normal stress. Whereas if you have this or this, yeah, this is also Fs and this is also Fs. So a dFs dAn would be a shear stress. This is the difference between a normal stress and a shear stress. And imagine a container of a fluid with a surface like this, either a solid or a fluid. This is how you differentiate, and you apply a stress that's along the surface. In other words, like this, you apply a shear stress like this. Now a solid, as you would imagine, would be distorted, but not that much. It would kind of distort a little bit like this, yeah, but it would tend to snap back to its original position. It would snap back, right? Whereas a fluid, on the other hand, will not be able to withstand this shear. It will flow. A fluid flows. It cannot withstand shear. This is what characterizes, this is the fundamental thing that characterizes a fluid, right? So it cannot withstand shear, and more specifically, when you, in the same kind of situation, when you have, like so, and a fluid element, a fluid surface like this, and you apply some kind of a, say, wind blowing over the surface of a lake, or some kind of situation like that. Suppose this was a container filled with honey. So what would happen is, if you apply a force on the surface, the top surface, you can think of the top surface flowing with some kind of velocity. Suppose this was the y coordinate and this is the x coordinate, and you have an x directed velocity like that. So the top surface would flow fastest, and you can think of the next layer flowing, but not nearly as fast, flowing with a slightly reduced velocity. This also, say, ux1, ux2. The next layer would flow slightly reduced like this, until you come to the bottom where the honey actually sticks, and there's practically no velocity. And if you wish, you can also draw ux4. In other words, there is a dux dy that is non-zero. Yeah, there's a gradient. The ux varies with y, right? And so there's a non-zero, and this is what characterizes a fluid. There are two things: A, it flows under the influence of shear, and B, typically there's a gradient, yeah, in the direction that's normal to the direction along which the force is. There's a gradient of the velocity, and in other words, there's a non-zero, and this is caused by the fact that fluids have non-zero viscosity. Yeah, it's almost as if these layers of fluid are connected by little rubber bands like this, that refuse to let the top layer slide over the bottom layer. Okay, they kind of like solids in that they also try to snap back, but they cannot. Okay, so the stiffness of these rubber bands kind of define what the viscosity is. That it characterizes the viscosity rather, and so this was another thing that I wanted to bring forth before plunging into specifics, and in particular, if you write down this kind of a quantity, tau s on the left hand side, and dux dy, which we saw on the previous slide, there is a constant of proportionality, and this is called the coefficient of dynamic viscosity. And this is the shear stress. It's essentially force by area, just like pressure. And that brings me to my point. There's really no need to draw a distinction between shear stress and pressure. It's the same thing. Yeah, what you're really normal and what you're suppose we draw a little imaginary cube like that. There's really no need to draw a distinction between pressure and shear stress. It's really the same thing. Pressure would be force per unit area in this direction. Shear stress would be force per unit area like this and like that. So if we, for instance, if we call this tau, if I call this phase 3, if I call this tau 3, and if I call this tau 3, and if I call this tau 3, 2, simply because this is phase 3, this is phase 2, and this is phase 1. Okay. So the tau 3 would be the force per unit area acting on phase 3, okay, along the normal to the phase, whereas tau 3 would be the force per unit area acting on phase 3. Well, it's another component, and tau 3 is the force per unit area acting on phase 3 along the normal to phase 2. Right. So this is by the way, I think I made a mistake here. This is really not phase 1. I should not. Let me simply label phase 3 and phase 2, and that's good enough. Right. So the point is, it's useful to think of the stress as a matrix with the elements tau 1, tau 2, tau 3, and then other off diagonal elements like this. Yeah. So the diagonal elements are these, tau 3, tau 2, and so on and so forth. And the off diagonal element, and these are what you normally think of as pressure, normal pressure, and the off diagonal elements are what you think of as, so these are all shear stresses. It's useful. This kind of a description will be useful to keep in mind when we go further, when we study the momentum equation, which is simply F equals ma for the fluid. Okay, so I wanted to introduce this up front and introduce the concept of viscosity. So in each of these cases, for each of these shear stresses, there is this kind of a relation that's valid. Okay. You can think of a mu that characterizes each of these shear stresses. Okay. So the components of mu will also form a matrix, which we call a tensor. Okay. In this case, that's good enough. There's really no need to go into the into more detail about what a tensor is. You can simply think of it as a matrix, and it's the same way one thinks about elasticity for solids. Right. So this was the other key thing we talked about, and from now on we will start talking about the kinematics of fluids. That's mostly what we will talk about from the next session onwards, which is focus on the appearance of motion, such as displacement, velocity, acceleration, so on and so forth, of fluid elements, without explicitly talking about the forces that are acting on them. We are really not concerned about an F equals ma, a conservation law, but instead we want to see the manner in which the fluid is moving or not. Yeah. So we will talk about concepts like streamlines, path lines, and so on and so forth, which will be very useful when we go ahead. So from the next session onwards, we will start talking about fluid kinematics.